Good afternoon. I'm Dick Karp, the director of the Simons Institute for the Theory of Computing, and I have the pleasure of introducing Professor Giorgio Ottaviani, who's been visiting us this semester and will remain through the end of the semester in the program on algorithms and complexity in algebraic geometry. Professor Ottaviani received his PhD from the University of Florence in 1987. He spent some time at the University of Rome and the University of Aquila before returning to Florence. In 1989, he won the prize of the Severi Foundation, a prestigious prize in the field of algebraic geometry. He's worked in a number of areas of algebraic geometry and mentions in his, somewhere in his biography that he enjoys the use of computers in connection with that field. For the last 8 years, he has been focusing in particular on tensors and tensor rank viewed from a geometric point of view. And he's been studying the applications of tensors in complexity theory and also in algebraic statistics. And today he promises to give us an introductory exposition of tensors from a geometric view.
Okay, many thanks for this kind introduction, and I also take the opportunity to thank very much the Simons Institute for all the opportunity. We had several people all around the world to meet with this program in complexity in algebraic geometry, and tensor, I think, was one of the relevant parts of this program. So this is a very brief plan of what I want to cover. So I will start with the introduction to tensors, and then I will focus on some relevant application, some of them also related to the activity we had at Simons. I say immediately, I of course cannot cover all the aspects. For example, I like a lot complexity of matrix multiplication, but there will no time, and already there was the excellent lecture by Peter Burgisser, which was focused mainly about this theme. Okay, so of course interrupt me and ask me question any time, especially on the definition and the notation if everything is clear from the beginning. I start with the picture. I will try to do many pictures. So this is a 2 times 2 times 3 tensor, which is just a 3-dimensional generalization of a usual matrix. You can fill every box with an element, in this case of the complex field, but of course also other fields can be useful. But from the very beginning, let me say that since this is a tensor product of vector space, we can act with linear change of coordinates on each factor. And so I am interested not only to the property that you see from this box, but to the property which are invariant by this change of coordinates. Essentially, following Klein geometry means the study of the property invariant under some group which act. Okay. So I continue here the matrices versus tensor. Matrices have row and columns, and in tensor you have slices. And you can immediately see that in this case you have at least 3 types of slices. 2 are shown, and there is a third one that you can easily image by your own. And now I come to matrices. If you want to, for example, compute the rank of a matrix, the most common algorithm is Gaussian elimination, that you start, if this is a matrix I color all red, I mean that the elements are general ones. And if you want to perform Gaussian elimination, what you do? You pick the first column and you add to the column, you add to the other rows in order that you can make 0 the elements which are here. And in my convention now, a white box is just a box with a 0. This will be for all my talk. So you can go on easily, then with some assumption you arrive here, and you can immediately say that the rank is 5. But now you can go over and also doing Gaussian elimination backwards. And if you act on rows, this is the best you can obtain. But now if you also want to sum columns, you can do better. And you arrive to this, say, canonical form when only the red one are non-zero. All the matrix has been empty. And let me see. Oh, sorry, I was too quick. Let me underline this matrix is of rank 5. It is the sum of 5 rank 1 matrices, which correspond exactly to these 5 red boxes that you see. And since you act always by group action, you can go backward. And also the original matrix is a sum of 5 rank 1 matrices. That's quite interesting. And now try to do the same for a tensor. So just to start, we have to define and understand what's a rank 1 tensor. So for matrix, a rank 1 matrix is just the product of 2 vectors. I think this picture should be self-explainable. And here is a decomposable tensor. I think, and I hope also this notation should be quite clear. As the product of these 3 tensors, I get this matrix when only the red box is non-zero, and I stress that all the white ones that you see are just 0 entries. Question up to now? OK. Just the difference between 0 and non-zero. So I try now Gaussian elimination on this Rubik cube. It's 3 times 3 times 3. Then I choose this starting point, and I want to make 0 after. Well, you can, if you just take the first horizontal slice and you sum back down, and you get easily this one. Then you can try to imitate the process you did for matrices. And on this slice, you can find essentially a canonical form. Now what you do? Well, on this slice, you cannot have better. You want to change. Like you want to find the cubic Rubik cube, which, by the way, I am not able to solve. But you want to try with this other slice. And you find in this way some 0, some other. Well, I confess now I'm a bit stuck. What else to do? Because if you try to do some other slice sum into another, you can easily destroy what you already have obtained. So one has to think a bit about this problem. How many 0 may I get in such a matrix just with the slice operation? When Strassen showed in 1983, one remains with at least 5 non-zero entries, but even more, this theorem is geometric, so does not depend on the choice of coordinate. So you remain starting from a general with at least 5 decomposable summand. A decomposable summand, if I come back, is like this one. So the product of 1 vector, 1 vector, 1 vector, OK? Now you see again all the process, which is nice. And why this is maybe counterintuitive? Because this 5, well, it's much bigger than, not much, but it's bigger than 3. It's bigger than 3, and so you can say that a general matrix of this kind has rank 5, even if the dimension of all the individual factors is just 3. And well, I recommend this as a thing that Abel said, read the master, and in particular read Strassen. If you want to understand the basic about tensors, he wrote really very nice and seminal papers, and probably was the first one who applied geometric techniques in this study. So now I show a case classification quickly when everything goes fine. The 2 times 2 times 2 is probably the first non-trivial three-dimensional case. In this case, up to the linear action, up to linear change of coordinates, there are exactly 6 canonical forms. And you see the first 2 are quite interesting. Here you have 2 boxes extreme, and that means a general has rank 2. Here you have 3, and in this case the hyperdeterminant vanishes. Well, in 2000 appeared a paper in the physical literature that, if you check on Google Scholar, has 2,000 citations, and they rediscover this classification, which in the qubit language of physics and also of quantum computing is quite stimulating and interesting. And then you find other orbits, and this is the easy one of rank 1. But this is one of the few lucky cases when you can have such a beautiful and finite classification. So try now to think, change a bit the point of view, not only think at slices, but think to group action. So by group action, I mean that there is 3 GLN, 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 3 group of matrices which act on the 3 side of a 3-dimensional tensor, and the dimension of this group is 3n square, and 3n square is smaller than n cube. You see, this grows as n square, this grows n cube. The dimension of the space is bigger than the dimension of the group which acts over, so certainly you cannot have finitely many canonical forms up to this action. And now you understand also why the case of 2 factors was quite special, because for 2 factors, the dimension of the space already was n square, which grows like exactly the dimension of the group acting over. So this makes a problem, and we can maybe joke a bit that the matrices were so nice to be studied were created by the god, and the tensor were created by the devil. So one after this slide should stop, but we try to go on. And again, now I want to use geometry, so now tangent spaces, okay? So this is a rank 1 matrix. You have to think just as a point in the space of all matrices. And my question is, can you visualize the tangent space to this matrix? And this is the answer. This is the tangent space. And this is shown by Leibniz formula. And I try to explain why, explain some details. So if you want to compute the tangent space, what you have to do in a variety, you take a curve through the point and compute the derivative through the curve, and compute the derivative for all the curves through the point. So this is my curve, and I assume that for t equals 0, my curve arrives here. And now Leibniz formula gives that you have 2 summands when a prime of 0, b prime of 0 can be everything because depend on the direction. And so in the result, you get just this first vector space, which means this first column, and the second vector space, which is the row, the second row. And if you sum together, you get exactly, I show you again this was the tangent space at this point, and clearly now you can draw tangent space for any of these. Now try to repeat for tensor. I don't write down the details, but you can imagine you can apply Leibniz formula, but now you have a 3 factor, and so the result is the following. This is the tangent space to that one-dimensional tensor, and well, this looks like the hypercube. These are better pictures, and that's a Salvador Dali. Now go on and do the same for rank 2 matrix. Again, I ask you, think geometrically, what's the tangent space here? And probably you can image the answer. And this answer is hidden in a very basic result, which is called the Terracini lemma. This computes the tangent space to all rank 2 matrices, and you just take the sum individually of the two. And you see that I've painted by blue 2 boxes because they are the intersection of the 2 tangent spaces. And this is actually what happens in the space. You have a tangent space here, you have a tangent space in another point, and they meet. Actually, they meet in a line. And here you see only 2 points on this line. And, OK, they meet here. Now what I have to do, so I try to repeat what I did. Tangent space rank 1 matrix, tangent space rank 1 tensor, tangent space rank 2 matrix, and so tangent space rank 2 tensor. And this is my rank 2 tensor. I draw the tangent space. You see that in this box I have 3 edges, and there is another box just opposite in the corner, and the tangent space again shows 3 edges. You don't see one because it's hidden. Do you see blue boxes? Are maybe hidden? No, they don't meet. They don't meet. OK, this very elementary fact that 2 tangent spaces for a 3-dimensional tensor don't meet, well, make, from some point of view, tensor even better than matrices. So again, joking, maybe the devil was sleeping, or maybe did by purpose such a thing. And in a while, I will give some application of this using the so-called tensor decomposition. This is a basic fact that guarantees that tensor decomposition is unique for tensor and is almost never unique for matrices. OK, so this was some compare about matrix and tensor. Now I want to study a small case that was done in 19th century by Kronecker and Weierstrass. So the tensor which have 2 slices in one direction, so 2 times b times c. And I want to show maybe from a non-conventional point of view this classification because it is quite nice. Anyway, the classification of this particular class of tensor can be done in 2 steps. Sorry. The first step is that there are canonical forma for 2 basic cases, 2nn and 2nn plus 1. Okay? And this latter one, the 2nn plus 1, is just a building block for all the other cases. So let's go into some detail. In the 2nn case, I can reduce, think now to a tensor just to the 2 floor. You have a building with the first floor and second floor, and I picked the floor, nice. But so this is just a pencil, so a pair of matrices when you have to act in the same way for adding rows or columns, so you have the same group GLN on the rows of both, GLN on the columns of both, and you always, starting from general tensor, can arrive to a simultaneous diagonalization, okay? That's, even you can get more that here all the diagonal elements are 1. Here did an exception, not only painted red, but even I printed what is inside, but the white one are always 0, okay? That's the second one. And in particular, you see there are moduli, because these can change. That's the classification of 2nn plus 1. And in general, you can arrive to this picture with a new phenomena that you have no more moduli. Always the scalar can be obtained by 1. So up to linear change of coordinates, you always get the same tensor. In geometry, we say there is a dense orbit on the space. And now Kronecker-Weierstrass show quite interesting fact that any other 2BC, with, we may assume that B is smaller than C because the equal case was already considered, it's always the sum of 2nn plus 1 and another with just 1n more. So let's see in some example, 2 to 4 can be always decomposed in the sum of these. And then 2 to 5, 2 to 6, 2 to 7, you just image here, you add, and what you add can be reduced by 0. And so you have always this form. So it's very, very simple, okay? And that's what happens for a 2, 3, 5. You see you have 2 blocks, 1, 2, 2, 3. You have, in this case, the 2 consecutive. Then you have a 2, 3, 6. And then again, you go to 0 forever. So also in this case, it's very simple. So, well, after this, you can ask, if I add the third floor, is there any simple classification like this one also in this case? And the answer is yes, but only if you are allowed to have a tensor in a big, big space. So one should be quite big. If you have 3 slices and you have a 3BC tensor, you have this nice classification. If C is bigger enough, you see this, the ratio between C and B in this inequality go to the square of the golden ratio, which appear indeed because you have Fibonacci numbers, or maybe the converse. Since there are Fibonacci numbers, appear the square of the golden ratio. These are odd Fibonacci numbers. So you see 3, 8, 21, 55. You are missing a 5, 13. And so it's like in the sunflower, if you jump of 2 steps instead of 1 step, and this explain the square. Here you see should be 1, 3, and 8 in this example. This is a nice theorem by Kach, was proved with the language of quivers, but it's possible to give also independent proofs. And it's possible to generalize this argument also to any number of slices, but of course you need inequality which are weaker and weaker in some sense. That one of the sizes of the tensor has to be bigger than the other one. For example, there is no hope to apply such a kind of result to the cubic case, so n, n, n. Okay? No, for any fixed n, there is a similar linear. Yeah. Of course, the scalar of the grows with n. So the linear means that the ratio between the two numbers goes, in this case, there is a 3 because there is a square of golden ratio because you have 3. If instead of 3 you have 4, 5, 6, this ratio increases, but is always linear. Yeah. So in some sense, it's not so terrible. You can classify quite a lot. But asymptotically is easy to show. The difficult part is show exactly that Fibonacci number appear in the first cases. Okay, some geometric view. Maybe I told you about tangent space, but I never had the picture. So in this picture, I draw, this is a rank 1 variety of any tensor. And if you have T as the sum of D1 plus D2, you can assume, if you draw projectively, that T lies on a line which join D1 and D2, which is called the secant line. And the variety of the composable tensor is a product of projective spaces. It was studied by Corrado Segre, takes his name in the 19th century. Tensor decomposition means that you write your tensor as a sum of the composable 1. The number of summand is the rank when it is minimal. And for tensor, this tensor decomposition is often unique. Unique means up to the order of summands. And so this means that you can recover the di from T. And usually this is not possible for matrices. And this is what I try to show, and depends just on the property of tangent spaces I showed before. The blue boxes for matrices, meaning that two tangent spaces meet. No blue box for tensor that the tangent spaces do not meet anymore. Okay, now we will see in a while some application. And just after the definition, you can state this amazing conjecture that has maybe 10 years now and is complete, maybe some particular cases known, but in general it is completely open. And it's quite a scandal that it is still open, because it's so basic fact that if it is true, should really give a lot of consequence. So this means that in the symmetric case, a symmetric tensor is just a polynomial. When you want to decompose as a sum of rank 1, you can use other polynomials. And so as a rank 1 polynomials is just the power of a linear form. The conjectures say, in other words, that for symmetric tensor, you can define a symmetric rank and should be the same as the rank defined before. The symmetric rank should be equal to the rank. A minimal decomposition can always be found symmetric ones. Very nice conjecture, should be an important to progress to solve it, but up to now is open.
Do you believe it?
Yes, I believe. Maybe I, I can. For example, for binary forms has been proved that this is already quite. Okay, try some application. So topic model. Now, sorry, this picture is a bit poor, but if you have a document, you can detect in it some relevant words, and you can try to understand. Maybe a computer one trying to understand automatically from some word what's the topic, on how many topic is this document about. So, for example, if you speak about football, there should be ball, field, and if you speak about biology, maybe there are genes and DNA and blah, blah, blah. So one should, like today, we have a so large archive of documents. For example, Wikipedia is a huge collection of documents, and we can try to understand the probability just by collecting all these documents that the word appear. And in this topic, in 98, one of the first probabilistic algorithms trying to recover the topic was done by Christos Papadimitriou at Simons. This anyway had anything to do with tensors at that time. And now in the workshop at Simons just a few weeks ago, it was presented a very interesting research by Bhaskara, Charikar, Vyaragavan. I'm sorry that I've not found a picture by Bhaskara, that, by the way, is the person who I spoke more with. And I could have taken a camera with me, but I did not think at that moment. And they have in archive a paper that proposed now in the workshop to use tensor decomposition for the topic model. And they stressed especially that you have to compute the probability for the occurrence of starting 3 words, or maybe 4, but not 2, just because the tensor decomposition for a 3-dimensional space is unique and is not unique for 2-dimensional. And then you use tensor decomposition. In this case, I was impressed that the dimension of the space when you have to decompose is essentially the whole English vocabulary or Italian vocabulary, so of size 10 power 4, 10 power 5, which I never used to work with. And they had a lot of nice results. Here is just a printing of the probability of the occurrence of some words just divided by the topics. So I will touch some things I cannot enter now in the details, but just to show the possibility of application. Now I show a second example. When a lot of people is together in a room, and maybe police want to detect some suspicious voice, that's a possibility that you have to put many microphones, and in every microphone arrive a summation of sound waves, and you want to recover the original speech of each person. Here in this model, I have a square case, a P person and P microphone, but it's possible also to have a rectangular one. And now I don't enter into the details, also because it is difficult now to show you a speech, but I want to show you how to solve this problem with tensor decomposition with images, which is essentially the same, because I can encode in a very similar way. So here are 4 pictures. They was taken by Nick van Evenhoven. They are all around Florence. We did a trip, and he was interested with the camera to make all these pictures. Then these 4 pictures has been randomly mixed, okay? So this is a simulation of the previous. And now you apply tensor decomposition, and this is the result. So on the bottom you see the original picture, and this is what has been recovered by the tensor decomposition algorithm. This is around a hill in Florence. You see, this is quite good, but if you go at the other pictures, you see much better the defect, so you can believe that is not completely fake. You can really see, but for example, here in the recovered, you see that this part was faked, reconstructed just by this. So there was a mixture that tensor decomposition was not enough. And also, that's, no, maybe that one is not so bad. So assuming they were really speech, I think that it was possible to understand 99% of what had been So another problem, if you have a stochastic matrix, so all the entry are probability, so positive number between 0 and 1, and this matrix come to the cross of row and column and the relative probability. By the way, a correlation here means that the matrix has rank 1. So the question is the following. If you know only some entries of a matrix, so if you have a partial knowledge, it's possible to add the missing entries so that the matrix has rank 1 and it is stochastic. So the entries sum to 1 and it is non-negative. And here is an example, this partial matrix, and here is the solution. In this way, it is unique, and well, you can understand probably that obviously there are some product to be performed to find the missing entries, and you see also there is a symmetric and unique solution. Okay, let me quote, this was also shown at Simons, a theorem which gives a nice answer and also quite easy to be understood, and by Kubias and Zivrosen, that there is a necessary and sufficient condition to do that, that is this inequality. This essentially is a norm of the diagonal entries has to be bounded by 1, and if it is equal to 1, then the matrix has a unique completion. In the previous case, it was indeed 1, if you sum the square. And why I show this? Because it's nice that this is a case that generalizes completely well to tensor, and this is the generalization to any tensor with the d modes, so d dimension, and you see there is this inequality which is necessary and sufficient condition again, and if in this formula you put d equal to, you means a matrix, and you just get exactly the statement before, and the proof go on the same lines. Okay. Now, a few words about the hyperdeterminant. So for matrix, there is the determinant. For square matrices, is it possible to define something analog for tensors? And there is very beautiful theorem by Cayley, so a 19th century theorem. I want to read with you the condition that a tensor can be reduced to this form is equivalent to some vanishing of a polynomial which is det and is an hypersurface which we call the hyperdeterminant. But look at this picture. If you follow me, you have already seen this picture before. What is this? I show you when the tangent space, very good. But do you see something special here? The picture of tangent space have different colors. The colors were exactly reversed. Now there is white instead of red, red instead of white. So it's not a mistake. What does it mean, this? That this matrix has just these edges 0, and all the other can be non-zero. Why reversed? This is an orthogonality phenomena. Because if I multiply scalarly all entries of this matrix for a member of the tangent space, I get 0, because when there is white here, there is red in the tangent space, and the product is 0, and conversely. So this means that geometrically, I have a matrix which is orthogonal to the tangent space, and in geometry, this means you have a dual variety. So this shows that the matrices of this form make the dual variety to the variety of rank 1 tensors. And that's quite interesting because it gives a geometric, in pure geometric way, the definition of determinant, even for usual matrices. You can think that for usual matrices, have this white means just that the rank is not maximum, which is exactly the condition that the determinant vanishes. Okay, that's quite interesting. Anyway, computing a hyperdeterminant is much, much more difficult than computing the determinant. Now I have no time to enter into details, but this orthogonal situation allow me to quote this result of Elina Robeva, also obtained and shown at Simons a few weeks ago. And she gave the equation for the tensor that can be reduced to this diagonal form, you see, but only applying orthogonal transformation. So it's a theorem which works for orthogonal change. Okay? And, okay, this is the shape. And anyway, these are in general non-vanishing hyperdeterminants, so you never find the 3 edges which are completely empty here. That's interesting. Okay. And now probably this is the last problem I show, but I will try to give a bit more details, being the last one. So the minimum distance problem, in principle, to any variety, but I will apply to tensor soon. The picture means the following. You start from this point P. You see you have a parabola. The parabola is painted in red. And you want to check what's the minimum distance point from P to the parabola. And in this case is Q. And how you find Q? Well, you have geometrically to draw on a normal line. So this normal line has to be orthogonal to the tangent line in Q. Okay? And this blue one is the minimum distance you have from the point to the parabola. Now there is a very relevant case when this minimum distance problem has been solved. Not X a curve, but X the variety of matrices of bounded rank. So if instead of the parabola you take xk, the variety of matrices of rank bounded by k, now I will show you there is a theorem in mathematics that solves the problem, is Eckart-Young theorem. And you can perform explicitly this minimizing procedure by the singular value decomposition. So, oh la la, well, I think I already told you the relevant things. Well, there is maybe a name which is important. You find the best rank k approximation, the minimum distance to matrices of rank k. Now, singular value decomposition revisited from this point of view. The singular value decomposition of A is x dy when x and y are orthogonal and d is diagonal, and the diagonal has the singular values. Now, if you call x and y respectively the columns of x and the rows of y, then you have a sum of these singular values multiplied by rank 1 matrices obtained by rank and columns. So in some sense, if you sum for all sigma j, you get your original A. But if you sum on only some of them, you see the sum is only for j belonging to some subset of indices from I1 to Ik, then this is, of course, a rank k matrix. And this is interesting. It is a critical point of the distance function. So let me go back. This point Q was the minimum. But you see that on the other side, you can find another line that I've not drawn, which is again orthogonal. So this is again another local extreme. Could be minimum or maximum or maybe saddle, depending. But you can try to find all the local extrema, which I call critical point. Indeed, in this picture, if you do carefully, there are exactly 3 critical points. There is another here. And so the number of critical points in the matrix case, it's a binomial. And, 1 year ago, working with a group of people that was led by Bernd Sturfels, and then I will tell you in a while all, we are thinking that this binomial is very special because it has a duality as all binomial numbers. So when k is equal to m minus k does not change, it is the same. And so we try to understand if there was some duality hidden about this statement, and the result is affirmative. So let's go slowly. This variational principle of computing the minimum was extended from matrices to tensor already in 2005 by Lim Li Kang, and independently you get what is called an eigentensor by Li Kun Chi, and this eigentensor is maybe the proper way you should understand the paper by Olina Robeva I quoted before. You can compute how many eigentensor you have. This is Cartwright-Sturfel's formula. And we obtain a generalization with Shmuel Friedland in the case of non-symmetric case, you get the singular diuples. And let me stress these 2 formula were both obtained as application of algebraic geometry. In the first case, you use toric techniques, toric variety. In the second case, you have Chern classes and vector bundle. And so they are phenomena when algebraic geometry can give an answer in this multilinear setting. But both these computations have been generalized with the concept of Euclidean distance degree. And this is the bunch of people I told you before. This is Jan Drijsma, Emil Horobet, Bern, and Rekha Thomas. And the degree is something which can measure the complexity of computing the distance from an object. So if I take this chair and I want to understand how this chair is complex, well, maybe topology is not good because it does not measure some property. One possibility is the following. I try to compute my distance from me to the chair, and I compute all the extreme. And since the chair is very complex, I have a lot of extreme points. So counting all these extreme points can give a measure of how the chair is complex, and certainly give a measure of the complexity. That was the big word that I've not yet pronounced, of the complexity of computing the minimum from myself to the chair. And the Euclidean distance degree is just a measure of that. It's the number of critical points, and you can define from any variety. And it's not difficult to prove that if your point is general, so if I move from here to here, then the critical point change, but the number of them is fixed. And this number is the Euclidean distance degree. Of course, there are some technicality. This number is fixed on complex number. On real numbers can change. Now I have no time to enter in the details. And even for a projective variety, you can define, just looking at the affine cone and taking this count there. OK, this was quite an interesting topic for me that take this collaboration for several months very busy, especially because working with Bern, there is no time. So where is and but this topic was studied even before, and yeah, in this picture you see a line has Euclidean distance degree 1, a circle 2, the parabola should be 4, 3. Here is the ellipse, general conic is 4. And in this point, you see exactly the 4 normal. And this is nice because this 4 was computed by Apollonius in the 3rd century before Christ. But if you lie here, you have again a 4 solution, but 2 are complete conjugate and you don't see. You see only 2 which are real. That's a picture for the cardioid. In this case, Euclidean distance is interesting because it's quite small, because you have a big singularity. It is just 3, okay? And you find from here exactly 3 normals. And well, the green one is called the evolute, but now I have no time to enter into the details. I just want to conclude with the result of duality I promised before. There is a duality in computing the Euclidean distance. So if I take the dual of the chair, which is somewhere, and I can compute the Euclidean distance degree of that one by the Euclidean distance of the chair. And this is very important because sometimes the dual variety is easier to be studied than the variety itself. For example, the hyperdeterminant is a very unknown object, but to compute its Euclidean distance degree, it's enough to compute for the Segre variety, which is a product of spaces very well known and very easy to be studied. So this duality is important, and this theorem says that we have duality, and even more, you have an explicit bijection of critical points by X and X dual. There is a corollary, but I think that you can read by yourself, and I don't bother you because I'm going out of time. I conclude with a picture. Here you see this bijection of critical points. Given u, you get u minus x, and this is show exactly starting from u on computing over the red x, the critical points gives a bijection. X dual is the dual variety to x, and this is one of the critical points. So I stop here, and thank you for your attention.
Thank you for showing us those beautiful pictures. We have questions. Yes.
When I do matrices, quite often one thinks of by the geometry, things like linear transformations, and somehow not. And then, but when you say geometry for tensors, you sort of mean working with the symbol, this block of coefficients. So is there another notion of geometry similar to like the?
Yeah, you can use linear transformation, but for matrices, you have a clear way because you have 2 spaces and you divide. The first is the source, the second one is the target. If you have 3, you have more choices. You can take 2 of them as source and the third one as a target, but you can do in many ways. And you get a usual linear map in this way. You can study, and that's useful. This is called a flattening of the tensor. And this can help, but also I want to, this way is the first thing that people think to reduce multilinear algebra just to linear algebra. And it seems that you can do, but only to some extent. So probably it's not possible to reduce all multilinear algebra to linear algebra. Should be, so still I see a difference between God and devil in the joke I did, yeah.
Question about your application to the cocktail party problem. So how practical is the method? Like what is the complexity of using this technique?
Well, with the four picture I show you, it's really few seconds for a computer to do. A study of complexity, I confess, is beyond my expertise, and I even doubt if it was done in, well, in general, many computations regarding tensor are NP-hard. So there is a seminal paper by Li Kang Hiller. They show that computing tensor rank is NP-hard, and computing best rank 1 approximation is NP-hard. They have a lot of, and since tensor decomposition is NP-hard, so in general, since you need the tensor decomposition, but NP-hard, this means for the worst case. Maybe in the average it is better, but I don't think there is a, by the way, we were speaking with Peter just about that before. I don't think there is a study about that. Could be interesting project, yeah.